Welcome to the first part of Unit 9. In this unit, we're going to introduce the idea of circular motion and bring in the idea of universal gravitation. Part 1 is going to focus on uniform circular motion. We're going to begin by reviewing what happens when. So remember, if you look at this first set, the net force and the velocity are always opposite each other. This means that the object's velocity is going to decrease, or in other words, it's going to slow down. In the next set, the net force and the velocity are always in the same direction. This is going to increase the magnitude of the velocity, causing the velocity, the vehicle or object or whatever it is, to speed up. In the next four possibilities, the net force and the velocity are perpendicular to each other. When net force and velocity are perpendicular, that causes the velocity's direction to change, and it will change in the direction of the net force. So since the net force on this next one on the top row is downward and the velocity is to the right, then the path will veer off in that direction. As opposed to this one, which has a net force down but a velocity to the left, this one will turn this way. And if I continue this analysis with the other two, this one will go this way, and this one will go this way. Now, it is possible, for example, that you have a net force and a velocity that are not either parallel or anti-parallel or perpendicular. They're a combination, in which case you would get a change in the magnitude of the velocity and a change in the direction. But if you make things so that the net force is always directed perpendicular to the velocity, so no matter where you look in the object's motion, these two things are always perpendicular, right? What's going to happen? Well, the velocity's magnitude will not change because the force is always perpendicular to the velocity, so that only causes a change in direction. What will happen is you will see this thing constantly changing direction, and as it constantly changes direction, it will trace out a circular path. This scenario is known as uniform circular motion. It occurs when the net force is perpendicular to the velocity always, in which case the object moves in a circular path at constant speed. When this happens in this scenario, the net force takes on a special form. So normally we have Newton's second law that says F net equals ma. In this case, the net force becomes the centripetal force, and the acceleration becomes the centripetal acceleration. The centripetal acceleration has a special form, and that's given by the velocity squared divided by the radius of the circle. Okay, or the speed squared divided by the radius of the circle. Okay. So the last thing we're going to do is we're going to look at, well, what direction is the velocity in? What is actually going on? And for that, we're going to look at this PhET simulation. Here we have a ladybug sitting on a turntable. We can, that's not exactly what I want to do. Let's try resetting that. What I want to do is increase the angular velocity a little bit. Maybe a little bit more. Let's see what happens if we scroll down. Aha! There we go. So if I make this a little bit bigger, now we can see it turning. Okay, there we go. Now we can see all the controls. So you can see the ladybugs going in a circle. The velocity and the acceleration, therefore the velocity and the net force, are indeed always perpendicular to each other. The acceleration points inward towards the center of the circle. So will the net force. The velocity is always pointing perpendicular to the path, the circular path. That direction is known as tangent to the circle. So you may remember from a math class that a line that is tangent only touches a curve in one spot. This is a tangent. If I make it go faster, you'll see the velocity vector grows, but so does the acceleration vector, because it takes a larger net force to move something faster at the same radius, v squared over r, remember? Okay, so now let's pause this for a minute. We can toss the other beetle on, which apparently causes it to move again. Okay. So there you go. You can see they're both turning together, but because one is further out than the other, he has to move faster to do this, to do the same number of revolutions in the same amount of time. Okay. A good example of this, if you think about bands or military units that are moving in a circle, the people on the outside of the circle have to move faster than the people on the inside in order to have the whole line move together. If I change the direction, you'll see the velocity will change direction, but the acceleration is still pointed inward towards the center of the circle. Okay, so now going back to PowerPoint. So what direction is the velocity? If I have an object moving in a circle, where that dot is the center of the circle, so we'll make it a bug because that's what we were just looking at. His velocity will be tangent to the circle at any point on the circle. His acceleration will point towards the center, and because the net force and the acceleration point in the same direction, the net force will point in that direction as well. This concludes this unit, this part of this unit, I should say. In the next part, we will do some examples working with uniform circular motion.